Alright, so we are going to start just going through these equations, and we are going to use a pen to help navigate. Alright, so here is a top view of the vehicle. Here are front wheels. I'll assume they don't slip. I'll assume that the wheel steer axis is exactly passing through the ground contact point, which is C, and coincides with, in this picture, with the point P in the top view. The center of mass is symmetrically placed, that is G. Is steer axis passing through the contact point. The orientation of the vehicle is given by this angle phi, and theta is some kind of, it's the steer angle. We will need some kind of slip condition, and so at the ground contact point C, whatever is the ground contact force will be related to the velocity of the wheel point touching the ground, um, with some small proportionality constant. It actually hides complex physics. Without it, it's just a kinematics problem, and so this is the simplest possible model. From what is known in the initial configuration, we know this forward heading unit vector, the sideways unit vector defined by the front wheels, and then the steer is, this theta is not really used in the equations. I've written them in terms of these unit vectors. So you think of this En as perpendicular to the wheel plane, and Et is along the wheel plane. The rear wheel motor torque achieves the commanded forward velocity, which is V, and we will ignore its dynamics because we don't know what its torque is. So what we will assume is that relative to the ground contact wheel point C, the velocity of P in this direction, which is the same as this direction, Et, is V. So this is really a statement about the the rotation speed of the rear wheel. We will assume there is no slip at the front wheel. Now you may wonder why I'm assuming that. I think that the slip at the front wheel will be less than the slip at the rear wheel for two reasons. One is, roughly speaking, the weight at the front and at the back, um, they are at the front there are two wheels, so it's divided. The contact area is larger, then the friction's better. Um, Also, the front wheel just rolls along and the back wheel is driven, so there are some bigger forces there, so on. So anyway, it's an assumption of convenience. I think that it is roughly backed by some kind of physics. So here we are, the velocity of the point A. What's the point A? The point A is this point here. The point A is this point here. Its velocity is forward because the velocity of this wheel is forward, the velocity of this wheel is forward. This whole part is a rigid body, so the velocity is forward. That velocity, here is some scalar VA times the forward vector EF. Remember that this also changes with time. All right. We will take this width to be 2W, and this is R1, not RT. We will take backward forces, resistive forces at the wheel, which it's not really at the wheel, it's the effective force at the wheel axle, but that's good enough. This distance is taken as B, this distance as H. These are geometrical parameters. So you see that this force I have not taken as known yet. This force I have not taken as known yet. Along this axis there is a net force L, and this force from the ground on the wheel contact point C is Fc. Ignore this, that arrowhead was wrong. It's in this direction, is a vector force. So that's 1, 2, 3 scalars and 2. So there are 5 scalar unknowns that I have introduced so far. Now, when I take these forces and write linear momentum balance in the horizontal plane, so I have the two wheel forces that are backwards, the sideways force and this force. These are all the horizontal forces. This is mass times the acceleration of the center of mass. This is a vector equation in 2D, so that's two scalar equations. Angular momentum balance is in 3D, it is three vector equations, but over here, because it is planar motions, there is only the angle of rotation phi, and there is a scalar moment of inertia only, which is the z component of the moment of inertia tensor about the center of mass. We will take moments to be positive if they are counterclockwise. If I have not made any mistakes, the force at the left wheel provides a counterclockwise rotation. This one provides a clockwise rotation. This one provides a clockwise rotation. This I have to take a dot product with the, this is the vehicle related one and not the wheel related one. ES is this one, you see. So whatever is the force there dotted with ES times that distance, that's the moment. This J phi double dot. This phi double dot is an unknown, right? It's part of the job of the equation of motion to predict phi double dot. We'll do kinematics. The velocity of A is this because the front wheels don't slip. Then the acceleration of A, we take a derivative and it is, VA dot EF plus VA EF dot, but EF dot is minus phi dot ES. This is basic kinematics. So, and the acceleration of G, and this is the important part because the acceleration of G goes into this equation here. So the acceleration of G is the acceleration of A, which is defined in terms of this unknown and this known quantity, right? So this has one unknown, and then this is the centripetal term, and this is the tangential term, and here is the other unknown. So you see, in terms of my accelerations, I have a phi double dot and a VA dot. So I have two unknowns. This AG will go into this equation here. This is the angular momentum balance equation. Now, this is kinematics again. The velocity of point P is the velocity of point A plus this rotational term. If you go back to the first one here, the velocity of point P is the velocity of point A plus the velocity of P relative to A, which is due to a rotation like this, temporarily thinking of that as fixed because we are talking about relative velocity. So here we are. The velocity of P is given by this expression, and the velocity of P relative to C is given by the wheel rotation only, and the velocity of C, as we agreed earlier, is given by that slip constitutive relation, otherwise the problem has nothing. And this velocity of P relative to C from before is the rotation given by the wheel rotation rate. The velocity of P, therefore, is what? So I am writing this one here like this. So my slip constitutive relation has entered the equation. Please note that this constitutive relation is not during gross slip of the wheel. Over there, FC is known and VC can be, widely variable. It is only for small amounts of slip while rolling along on the path. And this epsilon is inversely proportional, roughly speaking, to the friction coefficient and the wheel normal force. But the wheel normal force varies as you accelerate and brake. It's not really a constant. This is just a fudge number. You put a small number there to understand what things can happen. So let's take stock. What do we know? At the start, the job of the equation of motion is to predict the derivatives of the velocities. So the velocities are known, the orientation is known, the position of the vehicle is known. What do we want to predict? We want to predict these motion quantities, but we also have these five unknowns that I had introduced. So it would seem like these five and these two make a total of 7 unknowns, right? But remember that by putting that equation 3 in 1, you can go back and look. We no longer deal with AG. So equation 1 and equation 2 are giving me 3 scalar unknowns, sorry, three scalar equations. And by putting 4 in 5, we have an equation for FC in terms of known things that gives me two scalar equations. Let's look at 4 in 5. If I put 4 in 5, VP is known from kinematics, and this is known from motor command, so therefore I know FC. So that's two equations. So then I have five equations, right? So we seem to be two equations short. This is because the resistance forces R1 and R2 cannot be predicted by Newton-Euler dynamics. They depend on the floor conditions. They are external inputs. The last time I wrote equations, I now remember, I took R1 equals R2, which means that the effective just passes through G, and I just took a known resistance force through G, if I remember correctly. Once you do that, you have five equations and five unknowns. That, then you do what you want with them.